Welcome back to Site 101X, the course on technology evaluation. This particular session is going to focus on laboratory versus field testing, serving as a guide for making that choice between the two options. I'm Dan Fry, and I received a lot of help on this particular session from Dan Sweeney as well as others. I want to cut to the chase here and show you what the consensus is of experts. This particular quote comes from the Global Alliance for Clean Cook Stoves, who have a lot of experience evaluating technology both in the lab and in the field, but I think their view is pretty broadly shared. And what they have concluded is that lab tests provide better ability to detect small changes because of the ability to control all the factors that would naturally vary in the field. But the downside of lab tests is that sometimes they give an inaccurate estimate of the actual performance of technology in the field. So let's explore those ideas both in theory and in practice. And I'll begin with a specific example of a lab test that was used by the Global Alliance for Clean Cook Stoves. They have defined something called the water boiling test. And that takes you through a specific sequence for every stove. You go through a cold start that raises the temperature of the water over a certain period of time. Then you go through a hot start, which brings the water to the same temperature, but perhaps a little bit faster because you don't have to heat up the cook stove itself quite as much. And the point is that the Global Alliance for Clean Cook Stove and their protocol tells you exactly what you need to do and how to control parameters like the way that the fuel is prepared, the way that the stove is set up, and also you would bring the stove indoors so that breezes and other variations would be under tight control. Now, there's also a well-defined field test for cook stoves, and the controlled cooking test is an example of that. It defines a set of procedures by which a stove is used to cook a meal. That is, to do the very things that people would actually do with cook stoves, except that some additional measurements are taken. And some things are controlled better than they normally would be. The same ingredients are used in each test, exactly measured out, and the fuel is also weighed and prepared carefully before and after cooking in a way that you wouldn't normally do when you're cooking a meal, but for the purpose of the test, it serves a purpose. And then, because the test is done in the field, there are some variations that you really can't control. For example, there might be breezes coming into the dwelling in one test and then not in another, just because one day it's a little windier than the last. So those variations may cause the measured efficiency of the stove to vary. Now, these ideas are related to three concepts that I want to review right now. First, there's accuracy. And accuracy of a measurement tells you how close your estimate will be on average to the true or reference value. So this reference value here is meant to indicate the value you should get from any kind of measurement if you have very precise and accurate values. This is the true value. Now, if you go out into a setting, either a lab or the field, you would see some degree of variation. And that degree of variation that you see would be able to be removed to some extent by taking an average. So you have a whole population of measurements that you have taken, which exhibit variation, and now you compress them down into a single value, the expected value or average, and to the extent that the expected value differs from the reference value, that's an indication that there is an inaccuracy of the measurement. Now there's another concept called precision, and that tells you about the range over which the measurements are likely to fall. So here we take that probability distribution and we cover a certain range of or a certain amount of probability density, And let's call that range the precision of the measurement. Now, if the variables are controlled very carefully, you might be able to shrink down the variations that you observe, but that may still leave a large gap in accuracy. So there's very different concepts here. Both precision and accuracy are important, but they're different ideas. Now, resolution is a third idea, also relevant to lab versus field tests, and it is the smallest difference that you can detect. So let's say, for example, that you're assessing cook stoves and you make a little change, maybe another path for airflow, and you ask yourself, could I even detect correctly whether or not that improved the efficiency of the stove? And if you have a high precision measurement procedure, you have a better chance of detecting small changes, therefore you have high resolution. Now let's talk about these ideas of accuracy, precision, and resolution in the example of a real-life measurement to show that they're not just theoretical considerations but practical considerations. MIT's D-Lab conducted lab and field tests on a charcoal stove. Here in red are the field tests, and here in blue are the lab tests. Now there are error bars on the lab test showing that there were variations, but the error bars on the field tests are wider, which is what we expect. We tend to see more variation in the field. Now, in this case, the error bars on the field test are so wide that they actually contain the average value in the lab also. So we don't know if there was a significantly large difference, statistically speaking, but it wouldn't surprise us if you measured enough values in the field. If you had large sample sizes, you could reduce the error bars to a smaller range, and you might find that there is a statistically significant difference between field and lab results. Now, let me show you an example in which the D-Lab ran lab results and also field results in two different locations. So here, for example, are tests from the natural draft TLUD and from the forced draft pellet cook stove design. And there's a pattern here that I want to point out. At the location here indicated in blue, we see that the efficiency was higher than it was in the lab. Now, by comparison, in this other location indicated in yellow, the efficiency was lower than that observed in the lab. Now, this same variation or this same pattern was observed also with this cook stove over here, the forced draft pellet. The blue bar, this location, indicates higher efficiency than in the lab, whereas this location with the yellow bar indicates lower efficiency in the lab. So the takeaway here is that we can't really predict which direction the difference between lab and field tests will go. It may depend on location. So it's very difficult for us to know whether the field is the more challenging condition for a particular technology or whether the lab is actually a more challenging condition for a technology to demonstrate its absolute performance or its benefits compared to the alternatives. Now, it seems clear to me why it is that we tend to see more variation in results when they're done through field tests. But it's an interesting question. Why is it that we tend to see different results on average even when we run repeated measurements? And one of the reasons is a phenomenon I call expectation shift. In the paper that I'm citing down here that I wrote in 2011, I describe the idea that when you have variations in some random variable X, like let's say breeze when you're testing a cook stove, those variations cause changes not only in the repeated measures, they cause not only spread here in the observed values Y, they also cause a shift. So what you see here is that there's a difference between the average over Y the expectation operator over the function y, and the function y applied to the expected value of x. So what we see is that when we allow variations to occur, especially in the field, that causes not only variations over here, but also a change in the average value that we observe. And in this paper, I show how to compute that shift. Now, let me summarize and tell a little bit about what this all means for how to choose between lab and field tests and what the other implications are. We recommend that you use lab tests if you have to make fine discriminations among alternatives, such as when you're engaged in a design process and you have to know if the design changes you made improved efficiency or not. We recommend that you use field tests if you need to make an unbiased estimate of the actual performance in a particular setting. And remember that the actual performance may change from setting to setting. Also keep in mind that when you won't be able to control variations, and that's especially true for field tests, you should plan for larger sample sizes, because larger sample sizes allow you to shrink error bars on an estimate even in the presence of variations. Or instead, you could plan for your study to detect only large effects, because large effects can often be discerned even with small sample sizes, even in the presence of large variations, if they're large enough to pop out and become visible to you. Now let me close with some photo credits for the images that I showed you here. And let me reemphasize, as always, that it's important for you to do the exercises that are associated with these segments so that you really learn the material and that you can do these things for yourself. So please do allocate enough time for that.